So let's get back into the rhythm of things and let's try to name the following compounds. And remember, you only care about the prefixes cyclo, iso, and neo for alphabetical order. Everything else, you ignore the prefix when you're sorting in alphabetical order. So I'll do the first example just to get everyone back in the rhythm of things. So first, we're going to identify the longest chain. So 1, 2, 3, 4, 5. Now I have two choices, both of which have an equal carbon length. So I'll just count down one of them arbitrarily. So I have my first method of counting. Let me count in the opposite direction down the chain. And let's note the substituents at each position. So in red, I have a 3-ethyl, 5-methyl, 6-methyl. While in my dark ink, I have 2-methyl, 3-methyl, 5-ethyl. And which numbering method is preferred? Which numbering method is preferred? Which numbering method gives us the smallest possible sequential locant numbers? The method using the black ink. So we'd name this as 5-ethyl 2,3-dimethyl heptane. Does this refresher example make sense? And remember, the reason why ethyl is first is because E goes before M. Does that make sense to everyone? Is everyone comfortable with this example? So what we're going to do now is we're going to tackle, and I'm going to have you work on the following example. And remember, as long as you apply the systematic rules that we've covered, these more complicated examples should pose no issue to you. So let's identify the longest chain, and let's try to get some proposed names for the following compound. And don't be shy to use the annotate tool to propose a numbering system for our carbon locant numbers for this molecule. And we'll discuss this example in about 3 to 4 minutes. And again, just as a reminder, the annotate tool is accessible in the little tab called meeting options. And you can use it to write out and draw on this class whiteboard and both propose a name for this compound and write out some carbon locant numbers. And let's try to get some proposed names for this compound in the chat, or some proposed annotated carbon numbers using the annotate tool. And we'll discuss this example momentarily in about another 2 to 3 minutes. I'd like to see a few responses and proposals in the chat before we discuss. Does anyone have a proposed name for this compound? Would anyone like to propose a name or at least a carbon locant number for this compound? This one's a little bit more tricky than usual, but if you follow the same rules, you'll have no issues. So does anyone have their proposed name for this compound? Would anyone like to propose a name for this compound? So let's at least start off with some carbon numbers. So we start and we have 3 potential chains to choose from. Well, we identify the longest chain. So we're going to start counting from the bottom chain because it has the most carbons arranged continuously. Okay, now if we compare our next juncture, we have the longer chain on the left. So we're going to count down the left chain. So it appears to me that our longest chain has 10 carbons, since we want the longest chain with the most branching. Okay, we have 2 methods of counting. Okay, in red, we have 3,3-dimethyl. So we have 2 methyls. At carbon 6, what do we call this group?
Isobutyl? Is it isobutyl?
Isobutyl, yep. Okay. Also at carbon 6, we have an ethyl group. Any other side chains that we have? Okay, let's compare to our numbering method in black. In this case, we have 5-ethyl, 5-isobutyl, 8,8-dimethyl. Okay, and which numbering method gives us the lowest carbon locant numbers?
Red.
Okay, perfect. So now all we have to do is just sort these names, sort these side chains in alphabetical order. And remember, iso, cyclo, iso, and neo are considered part of the group name. So E goes before D, which goes before I. So then we have 3,3-dimethyl, 6-ethyl, 6-isobutyl, and this would be decane. Does this make sense to everyone? Any questions on this example? So as you can see, even though the structure looks intimidating, the way that the problem is solved, yeah. E goes before M, yep. Sorry about that. So let me swap that really quickly. So the methyl should go at the end. So it should be 6 ethyl, 6 isobutyl, 3,3-dimethyl. There we go. E before I before M. Perfect. And then we write the name of our carbon chain, decane. There we go. Perfect. The di prefix doesn't count, the iso prefix does count. And that gives us our complete name for this carbon chain. Any questions on this example? So let's keep going then. And what we're next going to talk about is this idea of molecular shape and Newman projections. This is a good time where if you have your model kit, you should take out your model kit because we'll be using it throughout this next portion of the lecture. So stereochemistry refers to the three-dimensional arrangement of atoms in a molecule. Carbon-carbon single bonds and other single bonds are rotatable in long chain molecules. Thus, molecules are constantly changing their orientation of atoms over time. Now, a conformation or conformations refer to a 3D arrangement of atoms for a given molecule as the result of bond rotation. So, for example, if we have the following carbon-carbon bond, we can rotate our carbon-carbon bond and in turn change the relative position of our atoms. So all we're doing is rotating our carbon-carbon bond. And as you see, we have a different 3D arrangement of atoms. Okay, so there are two main ways of looking at straight chain alkanes. The first of which is known as a sawhorse representation. The second of which is known as a Newman projection. And a Newman projection is a 3D drawing looking at the arrangement of atoms relative to a carbon-carbon bond. So allow me a moment to put together a sample. And at this time, you may want to set up and make a model of the structure shown in the notes. And I'll be showing you this structure momentarily using my camera. So I'm giving everyone a moment to put together a structure using their model kit. Okay, so let's pretend we're looking at a typical molecule, okay? So I have just arbitrarily labeled one set of hydrogens as blue, the other set of hydrogens as red, okay? So now what we're going to do when we're looking at it from the sawhorse perspective, so we're looking at it from a side-on perspective. So does everyone see how we're looking sort of down one of our carbon-carbon bonds at an angle? Does everyone see how we're looking at our molecule from a side-on perspective? Okay, so this is a sawhorse representation. So we have one of our atoms pointing towards us, the other atom pointing away from us, and we can look at the relative arrangement of our hydrogen atoms. Now, a far more convenient method for understanding the relationship between atoms attached to each of our carbons is the Newman projection. So in the Newman projection, what we are doing is we are looking smack dab down a carbon-carbon bond. Does everyone see from this perspective how we are looking smack dab down our carbon-carbon bond? So we're taking our eyes and we're looking down and we're looking at our green carbon. Okay, as you can see, we have carbons and we have a carbon in the front, which is shown right here. And our atoms and substituents in the front are drawn in front of the circle. So for example, in this perspective, if we're using our blue and our red substituents, we draw our front substituents in front of the circle. Does everyone see that? Does everyone see that right now? Is everyone following so far? Front substituents attached to our front carbon drawn in front of our circle. Now, for our back substituents, does everyone notice how we can't actually see our back carbon? Does everyone notice how the back carbon is sort of blocked out of view? So the back carbon isn't visible, but we draw all of the substituents attached to our back carbon as lines that are behind our circle. Does everyone see how we took this structure and by looking down a carbon-carbon bond, we generated a Newman projection? Now, Newman projections are a matter of perspective. Depending on what carbon you're looking down, you'll end up with a different front and back carbon. We can just as easily look down the other carbon and we'll end up with now the red substituents are in front. Does this idea make sense to everyone? Does this idea make sense to everyone? Okay, so it's really important that you draw your what bond you're looking down. That's why I draw this little eye. That tells me I'm looking down this bond, so I rotate my molecule such that I'm staring down with this carbon in front. Okay, it's really important you keep your perspective defined so you don't confuse yourself. Now, molecules will constantly convert between different conformations, and different conformations have different energies. Thus, to switch between conformations requires a different amount of energy to overcome the activation barrier. So all of these conformations have a slightly different energy and a slightly different activation energy to switch between these conformations. Okay, so let's talk about how to draw a Newman projection. Let's talk about the step-by-step. So first, you prepare a Lewis structure for your molecule, drawing all of the bonds. And then you prepare a model of your structure. So we already did that. We have our nice little model here. Just to make sure that the camera is functioning correctly, the blue is on the right-hand side, correct? You see the blue on the right-hand side? Okay. Okay, so now that we have our model, what we're gonna do is we're gonna rotate our model or our Lewis structure 90 degrees, so you're looking down the carbon-carbon bond. And then, just like we're gonna do a ton in this class, we're just gonna draw what we see, okay? So I started off with something like this. Now I'm gonna rotate it 90 degrees, and I'm looking down one of my bonds now, okay? So now that I'm looking down one of my carbon-carbon bonds, you draw the substituents in front of the circle. So we have our circle, we draw our front substituents, and make sure you draw their relative position. So we have a substituent pointing up, a substituent to the left, and a substituent to the right. In the back, we also have a substituent pointing up, to the left, and to the right. And we draw our back substituents behind the circle. Does this make sense to everyone? Front substituents in front of the circle, back substituents behind the circle. Does that make sense to everyone? Okay, this is partially why I asked you to get a model kit for this class. It's invaluable at visualizing the three-dimensional shape of molecules. So let's do some practice. I'd like you to draw a Newman projection for the following molecule. And I'm just going to arbitrarily tell you to look down this bond. So we're going to put in our hydrogens. Okay, and now I need to make a model kit of this. So give me a moment to put this together using my model kit. And during this time, you should also be putting together this molecule using your own model kit. Of course, the efficiently being able to put together and make models of different structures will save you time and focus your energy on actually solving the problem rather than just making the model. So let's put together a model for this molecule. Okay, so here's my rough sketch model of this molecule, where the black atoms are our carbons, the red are our bromines, and the white are our hydrogens. Does everyone have something pretty similar to what I have here? Does everyone understand where I got this model from, how I made this model? Okay, now following my guide, all I have to do is turn my molecule. I'm going to make this a little bit easier on me. We don't have to worry about the specific conformation we're drawing from for now. We're just turning our molecule 90 degrees and we just draw what we see. Okay, so what substituents do we have in the front? What substituents do we have in the front? And let's say their position. So in the front on the right, what do we have in the front right? Bromine, yep, so we put a bromine there. What about in the front left? What about in the front left? So let me make the lines a little better. What about in the front left? We have our carbon. Well, it's really a methyl group to be exact, but yes, the carbon. And then on the top, we have our hydrogen. Okay, what about in the back? What do we have on the bottom in the back? What do we have on the bottom in the back? Hydrogen, yep. What do we have on the right in the back? Bromine, and then finally our methyl group. Okay, does everyone understand where we got, does everyone understand how we generated this Newman projection? We just drew what we saw. Just draw what you see after rotating and looking down one of your carbon-carbon bonds. Does this make sense to everyone? Now, your exact Newman projection may be different. That's because you can draw a range of different conformations for this molecule. It's not unusual. So as long as you're able to correctly identify substituents on the front and back carbon, and you're looking down one of your carbon-carbon bonds when drawing your Newman projection, you should have no issues with this. Any questions on this example? Any questions on this example? Make sure to write out your hydrogens, though. You don't want to forget them, as they're critically important in the next part of this discussion. Can I get some confirmation in the chat that everyone's comfortable with this idea? Okay. So let's keep going now, and let's talk about conformational analysis. So in conformational analysis, we're assessing the relative energy of each conformation of a molecule. Now, we don't observe perfectly free rotation. There is a barrier to rotation, and some conformers are more stable than others. Now, this stems from the fact that atoms and side chains repel atoms and side chains in the same region of space. If atoms or side chains are close to each other, they experience a destabilizing repulsive interaction. Now, torsional strain is defined as that when you're rotating a molecule around a bond, the torsional strain is the repulsion caused by the electrons in between different groups when they pass each other. Now, there are a few different conformations that you'll need to be familiar with. The first of which is the staggered conformation. The staggered conformation is when you have all of your bonds as far apart as possible. And this is shown by a 60-degree dihedral angle, which is the angle separating your front and back substituents. The larger your dihedral angle, the farther apart your substituents are in three-dimensional space. So for example, if we're looking at a staggered conformation, does everyone see how if we look at the three-dimensional space between this black substituent and our red substituent, the angle separating them is quite large. This is known as the staggered conformation. Generally, the staggered conformations are low in energy because they minimize repulsive interactions between your substituents and bonded atoms. Now, the next major conformation is the eclipsed conformation. It is typically the least stable and the highest energy conformation. It's where all of our bonds are as close as possible to each other, and we have a net 0-degree dihedral angle. So, as you can observe, we have a significant amount of torsional strain as our substituents and our bonded atoms are brought in close proximity in terms of dihedral angle during our rotation. So the way that I like to think of torsional strain is as we are undergoing bond rotation, when we have a very small dihedral angle, there is a large amount of opportunity for our substituents to interact and engage in repulsive interactions. Does everyone notice how our two substituents are pretty close to each other in three-dimensional space? When we have a 0-degree dihedral angle, our substituents are quite close to each other. This in turn allows them to engage in repulsive interactions, which are destabilizing. raising the energy of this conformation. This is especially pronounced when we have quite bulky substituents, but it's even shown, and this torsional strain is appreciable even when you have eclipsing hydrogens. Okay, so there are a few other conformations that we'll discuss throughout this lecture. But the main thing I want you to keep in mind is that the difference in energy between the staggered and eclipsed conformations depends on the substituents. Now, one thing you can notice, if we plot our dihedral angle, so if we look at our dihedral angle, and we look at the energy as a function of dihedral angle, we have a series of eclipsed conformations and a series of staggered conformations. So essentially what we're doing in these graphs is we're looking at our molecule and we are slowly rotating. In this case, we're rotating our back substituents, and we're slowly rotating our back substituents in 60-degree increments. So 1, 2, 3, 4, 5, 6. And each rotation, each 60-degree rotation, we observe our conformation and we assess the energy. So we've rotated this back substituent, this back set of atoms 60 degrees by rotating our carbon-carbon bond. And then we assess the energy of this conformation. We rotate another 60 degrees. We assess the energy of this new conformation. And we repeat this process until we've rotated 360 degrees. This allows us to generate a graph of energy as a function of dihedral angle. Does that make sense to everyone? Does everyone understand how we're generating this graph? Now, as we can clearly see, the staggered and eclipsed conformations are degenerate. And in some cases, we have identical staggered conformations and identical eclipsed conformations. So for example, if the eclipsing interactions are identical, each of our eclipsed conformations will have the same energy. Does everyone notice how in this case, because all of our substituents are the same, we have the same energy for each of our eclipsed conformations? So when we have different substituents, we'll begin to see differences in our varying staggered and eclipsed conformations. Now, just to give everyone a tool to estimate some of these eclipsing interactions, the repulsion between substituents in the eclipse conformation is about 4 kilojoules for every hydrogen-hydrogen eclipsing interaction. So if we have 4 kilojoules per hydrogen-hydrogen eclipsing interaction, and we have 3 of these interactions, that would give us 12 kilojoules of torsional strain. And you're going to need to know these values because to understand and to quantify torsional strain allows you to compare the energy of different conformations and assign the lowest energy conformation. And this is important because the lowest energy conformation is often the conformation that's most accessible under standard conditions and is often the conformation that most accurately represents the molecule. And by looking at the low energy conformation, we can understand potential patterns of reactivity and potential trends in reactivity based on that conformation. Okay, so let's look at a variant now. We're looking at propane. So I'm going to need to make the model for propane. So just as a refresher, propane looks something like this. And when we write out our hydrogens, if we're thinking about the Newman projection for propane, we're going to look and we're going to arbitrarily choose to look down this carbon here. I'm going to put a star next to it. So let's make a model kit for propane and let's see what we can see. First things first, when you're doing a conformational analysis problem, I highly recommend just making a model for your structure. Let's put together a model of propane. Okay, here we go. So here's our model of propane. We are going to arbitrarily look down this carbon here. Okay. So as we can see very clearly, we have our methyl group. When we have our 2 hydrogens in the front and our 3 hydrogens in the back. Okay, so now what we're going to do is we're going to look at the different conformations of propane using our model kit. So the first conformation we're going to look at is known as the staggered conformation. Now, does everyone see how if we look at our methyl group, it is vastly separated in three-dimensional space from our back hydrogen? Does everyone see that 60-degree dihedral angle? Comparing the methyl group and our back hydrogen. Yeah, so we have a 60-degree angle. Okay, so what we're going to do now is we're going to rotate our back carbon-carbon bond and our substituents 60 degrees, and we now have our eclipsed conformation. Does everyone see how there is now a 0-degree dihedral angle between our substituents? How this methyl group and this back hydrogen are directly aligned. We have a 0-degree dihedral angle. Does everyone see that? Okay. Now, in terms of energetics, we know each of these hydrogen-hydrogen eclipsing interactions is 4 kilojoules per mole, while a methyl hydrogen eclipsing interaction costs us approximately 6.0 kilojoules per mole. So in total, for this eclipsed conformation, we have 14 kilojoules per mole of torsional strain. So one thing that I would like you to note is that if we look at rotation of our carbon-carbon bond, let's do another 60 degrees. So looking at the following, does this conformation look identical to our original staggered conformation? Is this conformation almost identical to our original staggered conformation? Yes, it is. So we have degenerate conformations of the same energy for our staggered conformations. Likewise, if I keep rotating my carbon-carbon bond, does this new eclipsed conformation look identical to my previous eclipsed conformation? Yeah, so we have degenerate, staggered, and eclipsed conformations. Okay, so that's important to keep in mind. So if we made a graph of energy as a function of dihedral angle, we'd start off at 14 kilojoules, then we'd go down and back up to 14. So 0, 60, 120, 180, 240, 300. So our graph would look something like this, where all of our eclipsed conformations would be these high energy conformations with 14 kilojoules of torsional strain, while all of our staggered conformations would be down here with relatively lower amounts of torsional strain. Does that make sense to everyone? This idea that we have degenerate staggered conformations and degenerate eclipsed conformations. And that's based on the interactions between our substituents. Does this idea make sense? Is everyone comfortable with this idea? Does everyone understand how I generated this graph? We just rotated our carbon-carbon bond and we looked at all of our interactions and how much energy those interactions and how much energy that torsional strain cost us. Okay, let's look at larger alkanes. Let's look at butane. So butane looks something like this, though we're gonna have to fill in our hydrogens. If we don't fill in our hydrogens, we'll get stuck on these problems pretty quickly. So now that we have an idea of what butane looks like, we need to make a model. So let's do just that. Let's make a model of butane. If you aren't making a model, it's going to be pretty hard for you to visualize some of these later structures. So it'll really save you a lot of grief if you start developing the skill of putting together a model and looking at the conformations. Again, just like before, we are going to look down our second carbon. And once we've put together our model kit for butane, we end up with the following arrangement. Does everyone see how both of our methyl groups have the maximum dihedral angle? How both of our methyl groups are separated by 180 degrees. And remember, where did we get this structure? We started out from our straight chain, and then we just rotated it so that we're looking down our second carbon. Okay, so one important thing to note is that this structure is a unique staggered conformation in that we have 180-degree separation between our largest substituents. We call this conformation the anti-conformation. And in the anti-conformation, we have a 180-degree dihedral angle separating the largest substituents. And the anti-conformation is typically the lowest energy conformation. Why? Well, we have the least amount of interactions between our bulky substituents. So continuing on with this idea, what happens if we rotate our back carbon 60 degrees? Well, then we end up with a structure that looks something like this. To match the one in the notes, let me rotate it the other direction. There we go. Now we end up with a structure that looks like this. And as you see, we have a few interactions at play. So first, we have a methyl hydrogen interaction. First, we have a methyl hydrogen interaction. The methyl takes up space and can interact and engage in torsional strain with our hydrogen. So this costs us about 6 kilojoules per mole. We have a hydrogen-hydrogen eclipsing interaction, which is 4 kilojoules, and a methyl hydrogen, which is about 6 kilojoules. Okay, so far, so good. But there are more than one different eclipsed conformation, and there are more than one different staggered conformations. And what we're going to talk about next are some very interesting conformations. Is everyone following along so far? Is everyone following along so far with this analysis? Okay. Whoops, one moment. Okay, sorry, I just noticed that the nameplate was, there we go. I just noticed that the nameplate was blocking out some of the view. Okay, so let's keep going with this example. So we're going to continue on with our conformational analysis. Now, if there are substituents on both carbons, we need to use anti and Gauche nomenclature to describe the different staggered conformations. So the anti-conformation occurs when our bulkiest substituents, in this case our methyl groups, are 180 degrees apart. This is the lowest energy staggered conformation. So this anti-conformation, we have a 180-degree dihedral angle separating our bulky substituents. Another conformation that we observe is known as the Gauche conformation, where our methyl groups are 60 degrees apart. This is the higher energy staggered conformation. Now, the methyl groups experience a steric interaction as the methyl groups are trying to occupy the same region of space. So we've seen our first eclipse conformation. Let's look at our Gauche conformation. So to showcase this, the Gauche conformation occurs when we have a 60-degree separation. Let me showcase this way. When we have a 60-degree separation between our bulky substituents. This way is better because it matches the notes. Okay, so does everyone see how our two methyl groups, have a 60-degree dihedral angle separating them? Does everyone see how these two methyl groups have a 60-degree dihedral angle separating them? Okay, now, does everyone notice how these methyl groups also take up a fair amount of space, right? They take up more space than your typical hydrogen. So these methyl groups are both trying to occupy the same region of space, and in turn, we have what's known as a steric interaction, where both of our substituents take up space and they're trying to occupy the same region of space. This Gauche interaction, so a methyl-methyl Gauche interaction, which occurs when these two bulky substituents are separated by 60 degrees, this Gauche interaction costs us 3.8 kilojoules per mole. So it's energetically taxing when you have bulky substituents in close proximity in space. Does that make sense to everyone? Okay, now let's look at our second eclipsed conformation. So let's rotate another 60 degrees. Let's rotate another 60 degrees. So we've been rotating clockwise 60 degrees each time. And if we rotate another 60 degrees, we end up with a very high energy conformation, because what is happening between our methyl groups? What is happening between our methyl groups? Are they staggered or eclipsed? Are these methyl groups close or far away from each other? Looking at our methyl groups, are these methyl groups close or far away from each other? They're very close, right? And that in turn leads to a methyl-methyl eclipsing interaction, which is about 11 kilojoules per mole. It's extremely taxing in terms of torsional strain because both of our substituents are bulky and there's a combination of torsional and steric interactions at play. And trying to jam these methyl groups close together in three-dimensional space is not very energetically favorable. Additionally, we also have our hydrogen-hydrogen eclipsing interactions, which cost us 4 kilojoules. Does this make sense to everyone? Does this idea make sense to everyone? So in this case, not all of our staggered and eclipsed conformations are the same energy. Yes, a Gauche methyl-methyl interaction is about the same as a hydrogen-hydrogen eclipsing interaction. But the key thing is eclipsing interactions are torsional strain, while Gauche interactions are steric strain. Torsional strain, bond rotation. Steric strain, it involves the size of your substituents and how those substituents interact in 3D space. So like these two methyl groups, for example, let me get this lined up. So like these two methyl groups are trying to occupy the same region of space. So there's a steric repulsion. While torsional strain has to do with, as you're undergoing bond rotation, how do the substituents and the bonds connecting our atoms interact and repel each other? Does that make sense? Perfect. So just to visualize the Gauche conformation once again. So the Gauche conformation occurs when we have a 60-degree separation between bulky substituents. And this is a steric interaction that costs us around 3.8 kilojoules per mole. This is known as a Gauche-butane interaction. And we will see this again in later chapters. So if we're looking at and we're performing an energetic analysis, on butane, we start off. So in this case, if 0 degrees, so we have our eclipsed conformation. If we rotate our back substituents 60 degrees to the right, we end up with a Gauche conformation. So we pay a penalty of 3.8 kilojoules. Next, if we rotate another 60 degrees, we end up with an eclipsed conformation. But this eclipsed conformation is lower in energy because the methyl hydrogen interaction. What is the penalty for a methyl hydrogen interaction? We've been talking about it a lot. What is the torsional strain associated with a methyl hydrogen interaction? 6 kilojoules, okay. So 6 plus 4 gives us 16. And then we end up with an additional 60-degree rotation with the anti-conformation. I find it's easiest to make these dihedral energy diagrams looking at the dihedral angle separating our bulky substituents. Does this energy graph make sense? Does this make sense to everyone so far? Okay, so in general, the lower energy conformations minimize Gauche interactions and torsional strain. So for example, let's focus on kilojoules. You don't have to memorize kilocalories. I don't like kilocalories as a unit personally. As we discussed, an HH eclipsing interaction is 4 kilojoules. A methyl hydrogen eclipsing interaction is 6. Methyl-methyl eclipsing is 11. Methyl-methyl Gauche is 3.8. You'll need to have these values memorized, and I'm expecting you to perform quantitative calculations and make graphs just like we did up here. So that's the expectation moving forward. So let's do an example now where we identify the lowest and highest energy conformation across the C3-C4 bond. Now, you may say, what's carbon 3 and carbon 4? Well, if we use our nomenclature tools at our disposal, we see that our smallest locant numbers occur with the following numbering convention. And so we're looking down the carbon 3 and carbon 4 bond. Okay, so let's add in our hydrogens now. And let's break out our model kit. Let's break out our model kit. So let's put this together and then we'll discuss once we have our model kit completely assembled. You don't need to put every hydrogen, but the more hydrogens you put, the easier it is for you to understand and sort of appreciate the molecular shape. So right now we're just putting together our model kit, getting everything set and ready to go. It may take you a few moments, as it's taking me a few moments to get everything set up. You want to make sure that your model kit's accurate, because if your analysis is using an incorrect model kit, it's pointless. Okay, so here is our molecule. Here is our molecule. So now what we're going to do is we're going to look down carbon 3, which is this one right here. Okay, so we're going to look down carbon 3. So staring down carbon 3. Oops, wrong way. That's valid, but let's follow the instructions of the problem. So we're looking down carbon number 3. So let me get that set up. Okay, so let's start from our straight chain. Okay, carbon 3 is the carbon with the methyl group attached. So we're going to look down carbon 3. So looking down carbon 3. Okay, now we're going to draw what we see initially in the front. So what substituents do I have in the front pointing towards me? What substituents do I have in the front pointing towards me? So what substituents do I have pointing towards me right now? Like, for example, what is this substituent on the left? What is that? It's the methyl. Okay, perfect. What about our substituent on the right then? What do we call the substituent with 2 carbons? What do we call the substituent with 2 carbons? What's our substituent on the right? It's an ethyl. Okay. I'm going to draw them using bond line notation to make it easier to appreciate the bulk of each of these substituents. Now, looking in the back. So looking in the back now, let me stagger this a little bit so it's easier to see. So looking in the back, what do we have in the back right? What do we have in the back right? What substituent am I holding? What substituent am I holding? An ethyl group, yep. Okay. What substituent do we have in the back top? What do we call this substituent? Hydrogen, yep. Okay, and in the back left, we have a hydrogen. Does that make sense to everyone? So this is our ethyl group, this is our ethyl group, this is our methyl group. Does that make sense, how we got this Newman projection looking down one of our carbon-carbon bonds? So again, just to show this one more time, we start with our long chain structure. We are asked to look down the carbon 3 to carbon 4 carbon-carbon bond. So we look down carbon 3 and then we just draw what we see. Does that make sense to everyone? Does that process make sense? Does everyone understand where we got this Newman projection from? Can I get some confirmation in the chat that everyone understands how we got this Newman projection and drew out this first Newman projection? Okay, so now what we're going to do, is we're going to identify our bulkiest substituents. So I'm going to circle my ethyl groups as they're my bulkiest substituents. And I'm going to look at energy as a function of dihedral angle, comparing these bulky substituents. So I'm going to draw a conformation where these bulky substituents have 0 degrees of separation between them. So taking my Newman projection, I'm just going to set it up. So my bulky substituents have 0 degrees of separation between them. All I did was rotate my front carbon-carbon bond 60 degrees, just to show you what that would look like. That looks like this. Okay, so now what I'm going to do is I'm going to assess the interactions. Now what I'm going to do is I'm going to assess the interactions. So I have an ethyl-ethyl interaction. If we had to guess, based on the fact that a methyl-methyl interaction is around 11 kilojoules, what would we expect an ethyl-ethyl interaction to be if they're eclipsed? Would someone like to take a guess? What would an ethyl-ethyl interaction be like? Approximately. Ethyl groups are a little bit more bulky, so it should be somewhere around 11, but a little bit more. Would someone like to have a ballpark guess? Yeah, probably around 13 kilojoules. That's a reasonable ballpark. We also have a methyl hydrogen interaction, which costs us how much energy? What is a methyl hydrogen eclipsing interaction? Methyl hydrogen eclipsing interaction costs us how much of an energetic penalty? 6 kilojoules. And then we have a hydrogen-hydrogen eclipsing, which costs us around 4 kilojoules. So just as a shortcut, so this conformation in total has 23 kilojoules of torsional strain. And because it has this eclipsed conformation has our bulkiest substituents eclipsed, this conformation is likely going to be our highest energy conformation. If you're looking for the highest energy conformation, you want to have your largest substituents eclipsed. However, we're still going to entertain the other possibilities. So we're going to rotate our back substituents 60 degrees, and we will draw what we see. Okay, so we're looking down. Oops, let me get this all lined up. So we're looking down our carbon-carbon bond. We're now going to rotate our back substituents 60 degrees. Okay. So now that we've done that, now all we have to do is just draw what we see. So our front substituents stay exactly the same. And our back substituents, as we've noticed, we have our ethyl group pointing down, and our two hydrogens on the upper left and upper right corner. So in this case, we would call this conformation a Gauche conformation because we have a 60-degree separation between our ethyl groups. My question to you is, what would a Gauche ethyl-ethyl interaction be around, given that a Gauche methyl-methyl interaction is around 3.8 kilojoules? What would we estimate a Gauche ethyl-ethyl to be around, roughly? Would anyone have an estimate? Ethyl groups are a little more bulky, so we'd probably want a Gauche interaction to be between ethyl groups to cost us a little bit more energy. And what value would that be, roughly? Around 5, yeah, that's reasonable. Okay. Any other interactions, any other major interactions at play? I don't see anything else, so we're good to go in that respect. So let's rotate our back substituents. Let's rotate our back substituents another 60 degrees. And let's draw what we see. So when we rotate our back substituents another 60 degrees, we end up with the following conformation. So our dihedral angle is 120 degrees. So we have our methyl, our ethyl, and our hydrogen as normal. And now we have our hydrogen, and our ethyl group. And this is another one of our eclipsed conformations. Let me redraw this one more time. So we have our methyl, our ethyl, and our hydrogen. We have our ethyl, our hydrogen, and our hydrogen. Okay, perfect. So this is another one of our eclipsed conformations. So in this case, we have two ethyl hydrogen eclipsing interactions. What would we expect an ethyl hydrogen eclipsing interaction to be, given that a methyl hydrogen eclipsing interaction is about 6 kilojoules? What would we estimate for our ethyl hydrogen interaction? Does anyone have a proposal? Approximately. I'd say around 7 to 8. Okay. Perfect. So now we take our interactions. We have two ethyl hydrogen interactions. So we have 7 times 2 plus our methyl hydrogen interaction. And that gives us 20 kilojoules of strain, compared to our Gauche interaction, which has around 13.8. Oh, sorry, which has around 5 kilojoules of strain. Okay, let's keep going. Let's keep going. And let's draw out another one of our possible conformations as we continue to rotate our back substituents another 60 degrees. And in this case, we are approaching our anti-conformation, which is the lowest energy conformation, where we have a 180 dihedral angle between our bulkiest substituents. So let's showcase that. So continued rotation of our carbon-carbon bond places our back substituents as follows. Does everyone notice in the following Newman projection, how our two ethyl groups, does everyone see how our two ethyl groups that I'm holding are exactly opposite to each other? Let me get this rotated just right so that the view is good. Okay, here we go. So does everyone see how our two ethyl groups, let me rotate this a little bit so it's easier to see with the camera. Here we go. So does everyone see how these two ethyl groups are separated by a 180 degree dihedral angle? How our two ethyl groups are separated by a 180 degree dihedral angle. Does everyone see that? Can I get some confirmation in the chat that everyone sees the anti-conformation? So now all we're going to do is we're going to draw what we see. So we have our methyl up top, our ethyl group in the front on the right, our hydrogen on the left, our ethyl group in the back is on the left, our hydrogen is on the right and on the bottom. Okay, so this conformation is known as our anti-conformation. And this is going to be our lowest energy conformation. Now, despite that, there are still some interactions present. What interactions are found in this molecule? What interactions are found in this molecule? What interaction do we have in this molecule? Or in this specific conformation? What interaction do we have in this specific conformation that we've drawn? Would anyone like to take a guess? I see 60 degrees between my methyl and ethyl. So what type of interaction do we have? We call this a methyl-ethyl. What's that interaction called? When we have two substituents that are bulky, that are separated by 60 degree dihedral angles. What do we call that interaction? What do we call that interaction? Don't be shy to respond in the chat or verbally. What do we call an interaction between two bulky substituents separated by 60 degree dihedral angle? This is known as a steric interaction, or more specifically, a Gauche interaction between a methyl and an ethyl group. Yep, a Gauche interaction is a steric interaction. And given that a methyl-methyl interaction, we said it's around 3.8 kilojoules, and we said that an ethyl-ethyl interaction was around 5 kilojoules. What would we estimate for our methyl-ethyl interaction? Roughly, what would we estimate for our methyl-ethyl interaction? What amount of steric strain would we expect, roughly, using these two values as a guide? What would we estimate it to be? Around probably 4.5 kilojoules. And that's the only interaction present in this molecule. That is why this anti-conformation is the lowest energy conformation, because it has minimized as much as possible our torsional and steric interactions. Does this make sense to everyone? So if you want to draw the highest and lowest energy conformation, your highest energy conformation is your eclipsed conformation, where you have your bulkiest substituents with 0-degree dihedral angle separating them. If you want to draw your lowest energy conformation, you draw the anti-conformation, where you have your bulkiest substituents separated by 180 degrees dihedral angle. Does that idea make sense to everyone? Does that idea make sense? So if you're only asked to draw the highest and lowest energy conformation, you can actually skip these other two conformations and you can just focus on your eclipsed and anti-conformations. I am showing you all of the conformations as a function of dihedral angle because it really showcases how we calculate torsional and steric strain and how we can justify that the anti-conformation is the lowest in energy while the eclipsed conformation is the highest. Does that make sense to everyone? Does that make sense to everyone so far? Any questions? So just for completeness, let's continue rotating our carbon-carbon bond. And this time, let's just try drawing it directly from the previous Newman projection. So I keep my front substituents exactly the same. My back substituents end up rotated 60 degrees. So in this case, I have a hydrogen-hydrogen interaction. Let me redraw this so it's a little nicer. So I have a hydrogen-hydrogen eclipsing interaction, which costs me 4. I have a methyl-ethyl eclipsing interaction, which we said I would expect it to cost us somewhere around 12 kilojoules. We have an ethyl hydrogen eclipsing interaction, which costs us 7 kilojoules using our estimates. And that gives us 23 kilojoules total. This methyl ethyl is probably closer to around 11.5. So we end up with around 22.5 kilojoules total. So this is a pretty high energy eclipsing conformation, but it's not quite as bad as our fully eclipsed conformation. So this 240 degrees would be our second highest energy conformation. Does that make sense to everyone? Does this analysis and how I drew this structure from my previous Newman projection make sense? Okay, and then finally, for completeness sake, at 300 degrees dihedral angle, if we rotate these back substituents another 60 degrees, just to fill out our diagram. we have the following we have a methyl-ethyl Gauche interaction, and we have an ethyl-ethyl Gauche interaction. The methyl-ethyl Gauche interaction we said was 4.5 kilojoules, and ethyl-ethyl we estimated to be around 5 kilojoules. So this conformation would have 9.5 kilojoules of strain total. So outside of these additional conformations, what I really want you to focus on is if the problem asks you to identify the lowest and highest energy conformation, your lowest energy conformation will have 180 degrees dihedral angle. It will have your largest substituents anti, while your highest will have a 0 degree dihedral angle, where our bulkiest substituents are eclipsed. As we can see, our highest energy conformation is eclipsed. Our lowest energy conformation is anti. I want you to be able to draw the other conformations as a function of dihedral angle, and that's why I showed them to you in this example. Does that make sense to everyone? Does everyone understand what's entailed in these problems? Do these problems make sense and where we get these numbers? Does that make sense to everyone? Any questions on these examples? So we'll pause and we'll end today's lecture session.